Now, can you see this PowerPoint?
Yes.
ممتاز. Okay. صباح الخير. My objective today to cover the other two types of relay technologies, like static relays and the numerical relays. Okay. In the static relays, I will cover the advantages and limitations. Already I've covered this, I'll go over it. The basic building, I will go directly because I have covered this. I will go directly the basic building blocks and examples of static relays. Okay. So static relays are relays that are built based on using static components, solid state components, which is transistors. You can use diodes, resistor capacitors, or op amps, whatever. All these are components that can be used to build static relays. Static relays, in a sense, that doesn't have moving parts. Okay. So a relay in which the design response is developed by electronic, magnetic, or other components without a mechanical motion. So even numerical relay also a static relay, which is based on build based on microprocessor. However, to classify the new technology from the static relays, which is based on op amp and transistors, they call this the last generation as numerical relays, because you can, in addition, it's built based on solid state components, but all the protections or functions are built numerically as a software, which makes it different than this generation of static relays. So that's why we have static relay, which refers to relays, or it's also static relays, also called solid state relays. So in this solid state or static relays are based on op amps, diodes, transistors, resistors, and so forth. Okay. So based on these components, using those components, we can build different types of circuits, like squaring circuits, phase shifting circuit, integrator circuits, coincidence circuits, level detector, logic circuits. I will show you how do we build these. And when we combine some of these circuits together, we build a static relay. All right. Let's say the squaring circuits. Now, if I have a sine wave and I want to change it to a square wave, okay? So how do I do this? How do I build this one? I can use a comparator, right? A comparator. So I compare the signal, okay, with a reference ground, okay? I can compare it with the ground. Okay. So, and this can be positive VCC or negative VCC. So the input here, which is the input, if the input is larger than the ground, which is the reference here, the output is positive VCC. This is plus VCC. Okay, which is maybe if the VCC is 10, will be this is 10. Or if the input lower than the ground, which is the reference here, then the output is negative VCC. This is the V output. So this is a simple comparator. Okay, I can integrator circuit or circuits. This is just the basics that you have covered in Electronics 262. Okay, I'll just go over them quickly. Now, integrators are made of resistors and capacitors and an op amp. Okay, And if I inject, this is E input, E input or V input, and this is E output. If I inject, now this is an integrator. This is the relationship of the output as a function of input. So E output is negative because this is input is at the negative part, inverting terminal, and 1 over RC integration of the input with T. Now if the input is a step like this, now I know how do I generate a step. Like I can also generate a step with, if you put the negative VCC as a ground, I'll get a step of, instead of negative VCC, I'll have 0 here, okay? Now, suppose I have a step input, and I integrate a constant. If you integrate a constant, will be a constant times t, right? So we'll get a ramp, okay? And that ramp, the slope of that ramp is 1 over RC, okay? So once the input gets 0 at this point, if you integrate 0, it will be a constant, right? It will continue constant until this goes, if this goes negative, this will go down. Okay, so this is how I use integrate. This is how I build integrators. Now, I can. There is also the other types of circuit building blocks. Like we call them coincidence circuits. Coincidence circuits. I want to know if I have two signals, signal 1 and signal 2, and I want to know the intersection or the phase shift between them. Okay, so I want to know are they in phase or out of phase, or they are where they are coincident the intersection between these two signals. So if I have signal 1, I know how do I square. This could be a sine wave, which is something like this. Okay? I squared it already. And I take only the positive. And I have another wave here. Okay, I squared it already. And I want to know this common, right? Are they in phase or out of phase, or what's the time difference between them? In this case, I can, these two signals, I can, add them, I add AND gates here to input 1, V1, and V2, AND gate. So I have AND gate and V out. Now if this is high, which is now this is high, and the second is low, which is here low, the output is low, right? Only when both are high, the output is high in this region. Where both of them is high, the output is high. So this is low, this is high, and when input 1 becomes low, the output is low. Logic. So this is how this is called coincidence circuits. We have a level detector. A level detector is a circuit where I want the input, if the input reach a reference level, E reference, then I want an output triggered. If the input not greater than, if the input is less than this, I want the output 0. Okay, so what I did, this is VCC plus. This is the VCC plus, and this is VCC minus, a negative VCC. So a negative VCC, I put it to ground, which is 0. So this is equal to 0, right? Now, if the input higher than V reference, the output will be the VCC. So the reference here, I got the reference by using a voltage divider. So E reference in this case, this is just a voltage R1 and R2 as voltage divider, where R2 I can change it. I can use a variable resistance for R2 to change E reference, because I'll change the voltage level. Now E reference in this case, right? E reference, I can change now. E reference is equal to what? Equal to VCC, a voltage divider, times R2, voltage divider rule, over R1 plus R2. In this case, I got, so if I can vary R2, so that I can vary E reference, okay? This reference point. Suppose the reference I want it to be, let's say, half VCC. So I'll put this R2 equal to R1. I got, this is 50. So I want to monitor this signal. So like an over voltage or over current relay, this is how this is my set point, a reference, my setting, and this is the actual current or actual voltage. I want to compare it with this, okay? Now, if the input is higher than this, so at this now I'm showing you here, this is I suppose I have a ramp signal as input, okay? And I know a ramp signal, and this is my reference value, the reference, the blue one, okay? Now, during the time when V input less than V reference, which is all this time, where V input less than E reference, if this is less than this, the output is minus VCC. So the output is 0. And when the V input higher than V reference, the output is plus VCC, okay, high. So in this case, the relay, in this case, relay trips. This is, I can use this as a trip signal, or which indicates this input has exceeded the reference and I want to take action. Okay. I have also other types of building other circuits. We call them shifting circuits, phase shifting circuits. Suppose, and we have different types of shifting circuit, depends on the phase angle, the degree or the value of the phase angle I want to shift. Now, if I want to shift input signal V input by an angle 90 to 180, I will use this block. This block is just a resistance here and a resistance with a capacitors here. Okay, this is ZF is representing the impedance of R and JXC here, or C. Okay, the impedance of this. Okay, so this is Z, we call it ZF, and this is just RN. Now, you can prove this, okay, that the output, okay, is the function of the input with the a gain times the input times the gain is this impedance divided by this impedance, and the angle between output and input will be from 90 to 80. So what would happen here, the output will lead the input by 90 to 180. I can choose 90 or 100 up to 180 by controlling this resistance. If this resistance is 0, then that will be J here, okay, which is 90 degree. If the resistance extremely large, okay, compare the capacitor, this becomes like the angle of this becomes 0. Okay, and so I have a shape shift from 90 to 180 degree, and so this is the when I want to get higher than 180 degree phase shift. Like suppose I want to get 120 degree, then I will go for this block where R and C is here and the resistance is here. Okay, and so for this block I get 180 to 270. This signal E out leads this signal by 182, depends on the value of the resistance I choose here. Similarly, this block will give me 0 to minus 90 degree. So this lags this by 90 degree. And this leads this by 90 degree. So we have different building blocks, okay, to create different phase shift. We have also a timing circuit. If I want to know the time at which the output reach a certain level, okay, so I want to create a time delay, okay, but I want to know that exactly at 1 second. And if I want to so a timing, I want to know the level of V out after 1 second. So that once V out reached to that level, I know I have reached 1 second. So that I can also use this one as a timing circuits. So the relation between the time. So this is just from also from electronics 2 stuff. I can find the output. This current should equal to this current. This current Vn minus 0 over R, which is V over R equal, and this current is the voltage across C dV by dt. And the voltage between this point to this point is virtually ground. So I get this equation. And if I integrate this, okay, with respect to time, I got this relationship. Now, if the input, so for this, I can, if the output reach the input, the time will be RC, okay? If the output is half of this, it means the time is half of RC, and so forth. Now, how can we use these building blocks that I have mentioned to build a relay? Now, I can build them using transistors and diodes and RC components. So on this circuit, suppose I want to build instantaneous overcurrent relay. Instantaneous relay, if the current exceed a current setting, the relay will pick up and trip the circuits. Suppose I have now a CT. This is the CT, auxiliary CT. Suppose I have now here, the main CT is here, and I'm monitoring the current in this feeder, and this CT is connected to my relay. So this is my, so I'm connecting the main CT to my auxiliary CT, which I want to, that feeds my overcurrent relay. So this current will be stepped further because, you know, these electronic devices, okay, I have to make sure that they don't get damaged, because if I have op amps, you are limited by the inputs, okay? So first steps, I want first convert that current into a corresponding voltage so that we can compare those voltage to a reference value. So the first things, so this first block as a protection to these components. This is like call it spike filter. Spike filter is just a filter, a low pass filter. Now, in case this current has spikes, because at the end I want to convert it to a DC. First of all, I want to convert it to a lower to a voltage, but also I want to convert it also to DC. So spike here, if the signal has, if the signal current has a spike, harmonics like this, I will filter them out, smooth them out by this low pass filter. Then I have a converter, okay, bridge, which convert this now AC. This is still AC voltage here, okay. So they converted to DC now, So that signal, instead of sinusoidal, becomes okay, full wave. Okay, so this is the output. Now the output also I want to filter it by using this smoothing circuits. So the output here will be like, okay, almost like this, smooth. So it's like, now this is the voltage correspond to this uh, sinusoidal current. Now this voltage, I want to compare it with a reference voltage. Reference voltage, I can use this resistor to as a threshold. Okay. Now, if the for T1, if the base voltage here, which is VR2, greater than V at the emitter, which is this voltage from here to here, which is adjustable by RB, the T1 will turn on. Okay, if this base is higher than the emitter voltage, and once this turns on, a current will flow in this path. Okay, from VCC will go here, will go to here. So once a current pass, then I have also a voltage from, there will be a voltage here, a drop. So that voltage will be different than this voltage. This voltage from here to ground, while this voltage at this resistors from this point to ground. So in this case, the voltage here, difference between VCC point across the emitter and this, will make this one transistor T2 work. And once turned T2 operate, there will be a current flow here. So will conduct, sorry, no, it's not here, here in the, and this is like an auxiliary relay, small relay, where once, now this means once this conduct, then VCC will be across the relay and relay coil. This relay coil will get VCC as voltage across it, and which make this its contact to close. Okay. So this is now instantaneous. There is no time delay. Once this voltage higher than this relay will trips. And if this input, which is correspond to the rectified voltage of this current, okay, less than that reference value, the relay T1 will not be on. If T1 not on, there will be no current flow here. It's off. Means that voltage at this point, and the voltage at this point, if there is no current flow, will be at same potential. If the voltage between this point and this point at same potential, this T2 will be off. If this T2 is off, there will be no voltage across TR. So TR, this relay will be open. Okay. So there'll be no trip signal. I can also, this is how I implement a relay using transistors, but I can use op amps to build other types of relays, like negative sequence relay. A negative sequence, if you know from Power Systems 1, that you can convert, right, from Power System 1, that if I have VA, VB, VC, or I'll say the currents, because I'm now an example. It's applicable also to voltage. So I know that IA, okay, IB, IC, okay. This is from Power System 1, okay. Now there's a relationship between, it says I0, I1, I2. And I0 is the negative sequence current, I1 is the positive sequence current, I2 is the negative sequence current. Now, any imbalance currents can be decomposed or constructed using these three currents components, the negative, the zero, positive, and negative. So this is the aim. I will not go just very fast. This is 1, 1, 1. This is alpha squared, and alpha here, alpha squared, where alpha is 1 an angle 120, and alpha squared 1 angle 240, or minus 120. So what I want to build a relay that measures a negative sequence, I2. So I2, from this, you can take the inverse of this, I2, I0, I1, and I2 will be 1/3. If you take the inverse of this, it will be 1, 1, 1. This is alpha squared, alpha squared, alpha times IA, IB, IC. Okay, so therefore, I want to build a negative sequence, a relay that measure the negative sequence currents, and if the negative sequence current higher than a level, a certain level, I want to trip. So I want to find I2, the negative sequence current, is equal to 1/3 of what? Of the last row, which is IA plus alpha square IB. What is alpha square IB? It is IB shifted by 240 degree. And plus the last one is alpha times IC, which is current IC but shifted by 120 degree. All right, so I want to implement this equation. Now what I'll do, I'll take IA as add it with IB but shifted by 240. This is 240 degree shift, phase shift. This is phase shift. Okay, and this is 120 degree phase shift. Phase shift. So I'll shift B by 240 degree and shift A by 120. Then I'll add the three components. I'll take 1/3 of them. That will, I can measure I2. So how do I do this? So I have the currents. This is IA. Okay. Suppose current in a feeder. This is IB. And this is IC. Now this currents already in the feeder, I want to use CTs to, okay, so this is current that goes to, this is also IC, but this is IC prime, for example. This is IB, I'll say IB prime. And this is IA, I'll say IA prime. Okay. So this is the same, this in phase with IC, except it is at lower magnitude. Now that current if I put a burden on this CT, I convert, this current will flow here. This current here is very, very small because the input impedance of op-amps are very, very large. So very, very large impedance with in parallel with R, the burden I will put across the CT, this is will be negligible. So the CT will see this resistance as the burden. So suppose so this current will flow here. And so that voltage across the resistance here correspond to, is proportional to IC and also in phase with it. So that voltage is proportional to IC prime, which is proportional to IC, and similarly for other currents. So I got a voltage proportional to each current, and they are in phase. Now I want this voltage, first I want IA, okay, so this is also a voltage IA times R, this voltage IC times R, and this voltage IB times R. These voltages, I want IA without shift, but I want to shift IB by 240 degrees. So what I'll do, I'll take IA, I'll pass it through a summation. This is a summer, right? This block is, okay. This is summation of amp. So the gain here is 10 over 3. The gain of this is 1/3. Okay, gain is equal to 1/3. And that's why 1/3 I want, because I want IA to be multiplied by 1/3. Okay, so I got here the gain of this is 10K over 30K is 1/3, 1/3. So IA, which is that voltage, I want to take, this is all of this, including all of this is, okay. So this has 3 input, input 1, input 2, input 3, and this is like a summer. I will sum these 3 currents because I need to sum the 3 currents. But I am summing here 3 voltages corresponding to the currents. But for IA, I don't want to create any phase shift. Only I want to have 1/3. Phase B, I want to create 240 degree. So I want to throw this phase B. I added a block, which is a phase shifting block here, RC, and resistance here. I'll get a voltage, okay. I got to throw, as you can see from these building blocks, which is here. Okay, I want to get a 240 degree, that this is leads this by 240 degree. So I use this block, which is RC with RF, okay, because I want 240, which is in this range. So as RC with, so with this value of resistance, I will able to create a gain, unity gain, but at the same time, the gain between output and input is unity, but the phase shift is 240 degree. That is leading this input by 240 degree. Similarly, I want phase C, which is this one, the input here for phase C, and the output here shifted by 120 degree. So I use a block of RC and R, which is I want to get to 120 degrees, so I use this one. Okay, so which is this block. So I got this output here, leads this by 120 degree, but the gain is same. I will also choose R and C, okay, such that the gain here, the gain is this impedance of this is equal to 1, unity. So at 60 hertz, if you can check, this is 0.1 microfarad, and this is the resistance K, this is resistance, check this at 60 hertz, I use 60 hertz for the values. If you at 60 hertz, this impedance, by this impedance you'll get a gain of unity, okay, and the angle is minus 60 degree, okay, of the gain is this impedance of this block. So if you take this impedance, that's 60 hertz. So this impedance over this, you get a gain of unity, because this over this is unity, and the angle is minus 60, but the output here, because shifted by 180 degree, I get to 120 degree. So plus 180, I'll get 120 degree. Anyhow, I got these the 3 input shifted, right, and added here. I got this, but the problem here, the output here of from the summer will be a negative of the summation of this. So it is like the input here is ICR plus IBR, okay, plus times 1/3 all of them, which is this. And also because I'm using inverting as input, so the output is inverted negative. And because now I want plus here, so I will use another op-amp which just with unity gain and to shift the sign. So the output here is a negative of the input this. So I'll get rid of this negative. So I got this. So this is an implementation of this equation. So I would be able now to measure if there is a negative sequence in the currents, and now if there is a negative sequence, now if this is it has a value, means I have a negative sequence. Now based on this negative sequence, I want to make now a decisions. Now for the negative sequence, let's say exceed, let's say 20% of the positive sequence, or exceed this value of current, then I want to trip. Then the second block will be a level detector after this. Okay, to make a decision now. If this is all right. So this is how I build using phase shifters and blocks, okay, and level detectors. I can build so many other types of relay using op-amps or using coincidence circuits, okay. I can build distance relays, differential relays, I can use time delayed overcurrent relays. There's so many types of relays I can build them. So there are infinite, there's extremely large number of examples I can present here. Okay, I'll go to the third generation, which is the last part of my presentation on the on this chapter, on the microprocessor-based relays. In the microprocessor-based relays, I already mentioned about their advantages in the previous class. So I'll go directly to the building blocks and the algorithms, okay? Which is the software part. So in the building blocks, a relays, a microprocessor-based relays. So the main heart of it is a microprocessor, okay, or DSP boards, okay. Now for microprocessor boards to function, I need to have analog to a digital converter, because microprocessor based on 001, okay, logics. So I have to convert the inputs into a digital signal so that I can manipulate them in the microprocessor. I need a memory. I need also to store the software, to store the settings, to store, okay, the coding, the protection function I want to build using, let's say, the microprocessor coding language. Okay. So because I have different inputs, the inputs here be coming from the CTs and VTs. Okay. Suppose I want to build a distance relay. I need 3 voltages from the VTs and 3 currents from the CTs. If I would like to build a differential relay, I need 3 currents here and 3 currents here. So the inputs here depends on the type of relay I want to build. So these are the inputs, analog inputs from the main VTs or main CTs. Now, the first stage I want to do this voltage. As I mentioned, the output of the main VT is 110 to 120 volt over √3 bare phase. This is the output of a main VT, but this voltage will damage the transistor, sorry, the microprocessor. So I have to scale it down to a level within, let's say, 10 volt, okay, or 5 volt, okay, maximum. So I have to reduce this scale down. Similarly, the current from a CT, although we choose a CT of ratio, let's say with that the output is 5 ampere or 1, but this is when the current at rated. When there is a fault, this current can go to 20 times, so it can go to 100 ampere. So 100 ampere, once you convert it also to a voltage, it will get damage also the microprocessor. I have to scale it down also. So the first stage, we call it isolation and scaling, where I have auxiliary CTs and VTs, okay, to scale down those voltages and that currents to a smaller value, to a level suitable for this. So this is the first stage where voltage and current are reduced further using auxiliary transformers. And this auxiliary transformer also will isolate this input from the output, magnetic isolation. Once I scale this input, let's say I change this from let's say 110 volt over √3 to, let's say, 10 volt maximum, or 5 volt, depends on. So then I can process this. So before I get to this level, I need to pass this voltage. Now this voltage is still AC. Okay, and this is maximum peak to peak is 10 volt. Okay, so I want to scale this. First of all, I want to pass it through a low pass filter to get rid of high order harmonics. Okay, and we call this anti-aliasing filter. And if you covered signal and systems, okay, or you talk the sampling theorem. In sampling theorem, if you want to sample this signal, analog signal, the sampling frequency has to be greater than at least, okay, greater than twice the maximum frequency in the input signal. Okay, so if the input signal has, let's say, 50 hertz, 120 hertz, and it has harmonics also. So if you want to extract the let's say I want to measure the fifth harmonic, which is 5 times 50, okay, 250 hertz. I want to measure it. So this is, I'm interested to measure the fifth harmonic. Now, if I want to measure the fifth harmonic, which is 250 hertz, I have to pass them to the microprocessor. Now, if I use now in the sampling, this I'm interested in this, so I will pass them through the low pass filter. So I want to use a low pass filter, okay, which has, this is its gain characteristics of a low pass filter. So this is the frequency versus the magnitude gain, H. So this is the corner frequency, FC, at which the gain drops to, okay, minus 3 dB. So the corner frequency, I will choose it to be higher than this. Because I want to measure the fifth harmonic, so I have to pass it through the low pass filter. So I'll choose, let's say, 300, okay, or 400 hertz. So I'll choose here 400 hertz. So my corner frequency has to be greater first than the frequency I want to measure. Okay, the highest frequency in the signal that I am interested to measure. Sometimes some application I'm interested only in the 50 hertz, like in distance relay. I'm not interested in the second or third or fifth. So the maximum frequency anti-pass is 50 hertz. So I can use as corner frequency lower than this. In other applications, I am interested in the high frequency components, like in traveling wave based relays. I'm interested in 500, sorry, in let's say 500 in kilohertz, it's 100 kilohertz components. So I have to I choose a low pass filter corner frequency higher than 100 kilohertz in order to pass it to the next stages. So this corner frequency will be chosen based on the frequency that I'm interested to pass in order to measure it in the microprocessor. So that, and I will try to limit all other frequency higher than the frequency I'm not interested in. So suppose now I'm interested to measure up to fifth harmonic. This is the fifth harmonic. And so I'm interested, so I choose this 300 hertz. So I can choose 350. I'll choose 350. Anything higher? No, anything higher than 350 will have a gain, very low gain. At 400 hertz, it will not pass. 1 kilohertz will have output almost zero. It won't pass to the next stage. So with this means when I choose a sampling the sampling frequency has to be greater than the frequency that I am interested in. This case, you go for FC. So I have to choose my sampling rate, not 350. I'll go at least twice as more as this. Okay. So 350 times 2 is 700 hertz. So my corner frequency has to be greater than 700. So I'll choose, let's say, this 1 kilohertz as my sampling frequency. Okay. So this is why do we this? We want to limit through low pass filter. We want to limit the frequency bandwidth. Okay, range that I want to pass, because already I have fixed this sampling frequency, so I have to limit my F maximum limit by using a low pass filter. So this is the limit after I this is the problem of aliasing. What happens if I not satisfy that F maximum is F maximum has to be less than half of F sampling. Now, if I didn't sample, suppose I chose I pass a frequency higher than half of Fs. Now, if I have an analog signal which is DC, like in this, in DC input, the frequency is 0, so it doesn't matter now. I can, even with one sample, I can reconstruct the original signal. If I have an analog signal which is 0.09 then Fs, 0.09 times Fs, still this is less than half. So this is the sampled values. So the sampled value, as you can see, they represent the original solid line. So the sample value the analog signal can be reconstructed again from the sample value. If you choose a sampling less than half, the analog signal is less than half or equal to half of the sampling rate, Fs. Now here, if I increase the sampling more than half, like in this case, the frequency analog signal, which is the solid line, is higher than half of Fs sampling frequency. So this is the dot 9 means the sampled frequency, the instant at which I took samples at a rate of fs. Now, as you can see, this looks like doesn't represent the original signal. It's like a signal at a lower frequency than the original. So this, I get confused now. Is this signal represent this low frequency or the original signal? So this is called aliasing effects. Okay, so the aliasing effects are like a low frequency component will show up as if it is, okay, exists, okay, and that leads to inaccuracy in measuring the magnitude of the original signal. I want to measure its magnitude, and to avoid this, we limit the frequency that will pass to the microprocessor so that it is not higher than half of the sampling frequency by using this, low pass filter, by achieving that fs has to be always greater than twice fc. Okay. Now then, because I have 6 channels, this is the sample and hold. Sample and hold is just you sample the signal and you hold it. Yeah. So if I have an analog signal like this, okay, this is the input here from the low pass filter. The output here will be something. Okay, it's sample, you hold. It's sample, you hold. Something like a staircase. So as if it's something like this, I have a switch with capacitor here, this circuit. This is a very sample and hold. Now, if the switch is off, the output here, V output is, and V input here. V input is the input here. This is, let's say, V in, and this is V out. Okay, if the switch is off, the output will be same as voltage at the capacitor. This is called hold. The output will stay held at the voltage across this capacitor. Okay, when the switch is closed, output will be same as the input regardless of the capacitor, and capacitor will charge to the input. So now this is called the tracking stage. Okay, where the output tracks the inputs. When you hold it, when the switch is off, means hold, it will be stay like straight line. If you close it, it will try to jump to follow the input. Then if you hold it, so sample and hold. So at the end you'll get this. Why I need sample and hold at the end? I want to convert this analog level to a corresponding digital value. So with this, I want to change this into digital. The output here, which is at this level, I want to convert to a digital value using analog to digital converter. But since I have only one digital to analog converter, so analog to digital converter, I want to use a multiplexer. So I'll pass one channel at a time. Okay. So I'll pass this channel, I'll convert it to then I'll pass this channel and this channel, and the microprocessor will tell once it's finished from converting channel 1, it will tell this analog converter to go to the next channel. Okay. And similarly, once I convert this to analog, I can use microprocessor to convert this signal to microprocessor. I can now, this analog digital signal, I can process it. I can know what's its magnitude, what's its angle. I can know if there is a second harmonic in it. I can check the so many things. I can measure its frequency. I can measure so many things here using the microprocessor. Now, relay can store the program that I want to. So once I get a decision that the voltage or current higher than a certain, then I will take this decision to an output module, which is just I want to close this contact so that the relay trips. Okay, or I can also the microprocessor need also a digital input from outside, like I want to know the status of the circuit breaker. Status of the circuit, is it currently closed or currently open? If it is open, there is no need to send a trip signal to it. Okay, so to monitor the status of circuit breaker, I need as a digital input to a microprocessor relay to know that status. So this status is high or low through optical transistor here. And or sometimes I want to know, did I receive a trip signal from another relay? So this goes also a digital input signal to a microprocessor relay. I have also this for memory. I will just finish within a minute. We have RAM and ROM. ROM, you store the program when the program that calculate the magnitudes, everything. All the programs here is stored in EEPROM, so that you don't want to lose them once you turn off the relay. While in RAM, once you turn the relay, it's anything here in the RAM disappears. So in RAM, the microprocessor use the RAM for manipulation of values, calculation, and so forth. Okay, in the RAM. And we have a communication boards where I want to maybe connect this to laptops where I can see the readings, I can upload my new software, I can so many things. As well, yes. Okay, I'll stop here, and I'll stop at this one. Inshallah, next class I'll try to complete this one. Okay. All right. Do you have any questions? Okay. I want you to go to now the black. I'll stop the recording.